everybody, this is Miss Pierce here. Today we're going to be looking at transformations of functions. So we're going to be shifting our graphs up, down, left, right, and reflecting them. All right, so to vertically shift the graph k units, we're going to have a function and we're going to add a value to the end of our function. If that value is positive, it's going to move the graph up. If that value is negative, it's going to move the graph down. Makes sense, right? Okay, so we're going to look at some functions here. For our purposes, we're always going to start with f of x. Okay, that's not always the case, or I think there's some examples with b of x here. Okay, but most of the time we're going to be starting with f of x just to keep it pretty consistent. All right, so let's take a look. I've got a function g of x, and it's going to be the values for f of x, and we're going to add 3. So let's take a look here. All right, I'm going to pick a point on f of x and a corresponding point on g of x, and notice that it moves up 3. Okay, so that's the transformation here, is it's moving up 3. When I look at h of x, it's my same function f of x that I started with, but I'm subtracting 5. Okay, so let's take a look. We're going to pick a different point on f of x and corresponding point on h of x, and notice now it's moving down 5. Okay, so when I've got that subtraction at the end, now it moves it down. So I've got an absolute value function, b of x, graphed on the axes. We're going to graph a new function up 4 units to create r of x, and we are going to graph it ourselves. After we're done graphing it, we're going to determine the value b of -4, which is an x value, what's the y value, and r of -4, what that x value or what that y value is at the x value for. Okay. So b of x, I'm going to start with this vertex here. I'm going to shift it up 4 units, and I'm going to make sure that I'm copying and pasting those other points as best as I can. Otherwise, I'm going to get some funky answers when I'm evaluating. Okay. I'm going to label this r of x. All right. So my value when x is -4 for b of x is +4. And for r of x, it's -4, 8. Okay, so notice that those y values are shifting up 4. So when I make this function rule, I'm going to say, okay, r of x is equal to b of x plus 4. That's what it would look like in function notation. All right. Now let's take a look at this horizontal shift. So to horizontally shift the graph, h units, now instead of putting that number on the outside, we're going to put it next to the x on the inside of the parentheses. Okay, so if h is positive, then it's going to move the graph left, and if h is negative, it's going to move the graph right. And you might be like, Miss Pierce, I think you made a mistake, but I did not. Okay, you might remember from Algebra 1 that we use this little trick that it lies inside the parentheses, and we'll kind of dive into that more in just a second. Okay, but that's a nice trick to remember. So we have 3 functions again graphed here. Let's take a look. So we've got j of x, which is f of x minus 7. Notice it's on the inside of the parentheses next to the x. All right. So let's look at j of x. Oh, I think I should have used purple here. Okay, that's okay. So we'll switch that up. So notice that it moved right 7 units. Okay, I'll kind of change this to purple also. Okay, so it moved right 7 even though it was negative. M of x is f of x plus 5. Okay, so let's take a look. We're going to use a different corresponding point here, and I do see it's moving left 5 units. All right. Now let's take a look. We've got b of x again. This time we're going to translate it 3 units to the right to create, I think this is a typo, it should say h of x. We're going to graph that, and then we're going to evaluate b of negative 4 again, which we already know is 4. We did that earlier, okay? And h of negative 1, okay? So let's move this guy 3 units to the right, making sure I'm copying and pasting all those points nicely. Beautiful, beautiful. Okay, call this h of x. So like we said before, this is the point negative 4, 4, and then it wanted us to look at h of negative 1, which is 4. Okay. So notice that our y values didn't change here, but our x values are different this time. All right, so the function rule in terms of b of x is going to be b of x minus 3, because even though it moved to the right, remember it lies inside. Okay, there is a mathematical reasoning for this, so I'll just give you like kind of a quick example off to the side here. So let's say, just trying to get a nice color. So let's say you have a function f of x equals x, okay? And you want to look at when f of x is equal to 0, okay? Well, that's easy. Well, you just plug in 0 for f of x, so your x value is 0, okay? So you're looking at the point 0, 0. Make sense so far? Now we're going to look at this function g of x is equal to x plus 3, let's say. Well, we're going to do the same thing. Let g of x equal 0. Plug that in for 0, or excuse me, g of x. Well, what is your x value equal? You guys know how to solve a one-step equation like this. Well, x is equal to negative 3. Oh, so even though we added 3 earlier, because we're moving it over to the other side because of inverse operations, now it's changing that x value in the opposite way. So we end up with negative 3, 0. So that's why the inside lies, because of those inverse operations. We didn't have to do that before with y because we didn't have to move anything over to the other side. All right. Now let's take a look at our reflections. So we're going to, let's get a nice orange. To reflect a function across the x-axis, we're going to negate the y values. So we're going to get opposite y values when we graph it here. All right, let's look at an example k of x. So k of x is going to be negative f of x. And f of x is that funky little black function right there. And you'll probably see that it is beautifully reflected over our x-axis. All right, so we're going to take a look at a couple points, like the point 7, 2. And k of x at 7 is negative 2. All right. And at 2, 0 for f of x, well, it's still on that x-axis, so we're still at 2, 0 for k of x. All right. And the last point I wanted you guys to look at is f of 0, which is 9, and k of 0 is negative 9. All right. So we're going to kind of notice something if you haven't already. So f of 7's 2, k of 7's negative 2. F of 2 is 0, k of 2 is 0, and f of 0 is 9, k of 0 is negative 9. Are you guys seeing it? That the y values are all negated. The y values are all negated, even though 0, when you negate it, it's still 0. But the y values are all negated. Were the x-intercepts affected? No. But were the y-intercepts affected? Yes, because all the y values are opposite or negated. Okay. Now, to reflect a function across the y-axis, we're going to negate the x values. So we're going to get opposite x values here. Okay, let's take a look at p of x. That's what we're doing. We're negating the x values. Okay, notice that it flips across. Oops, sorry guys, my screen froze for a second. Notice that the function, come on. Oh my goodness. Okay, sorry guys, my pen just stopped working for a second. So notice that the function is flipped across the y-axis. All right, and we want to take a look at f of 7 again, which is still 2. Okay, hopefully my pen works now. Okay, yes it does. Okay, so it's flipped across the y-axis. All right, so we're looking at 7, 2. Well, notice that p of negative 7 is also 2. Okay, f of 2 is still 0, and p of negative 2 is 0. The last one we want to look at is f of 0, which is 5, and p of 0 is also 5 because it's still on that y-axis there. Okay, so notice that our y values stayed exactly the same, but what changed here really this time was our x values were negated. Our x values were negated. Our x values, even though it's 0, were still negated. So were the x-intercepts affected this time? Yes, they were. Were the y-intercepts affected? No, because only the x values were negated or were opposite / negated. All right. And that's all for our transformations today, guys. Thanks so much.